Alright, from last time we talked about the formal power series, and today we're gonna finally talk about the convergence of power series. So we're gonna first recall some terminologies from a series of complex numbers, right? So given a sequence, we consider their series, which is, we define the series as the limit of the partial sums, right? And if we're given two series, right, with partial sums, if they're both convergent, then the summation of the terms is the sum of their sum, right? And we also have this is true just because by the convergence of sequences, right? And given a series of real numbers, non-negative numbers, if all the partial sums are bounded, then it converges, right? Because monotone bounded principle, right? Now we let an be a series of complex numbers. We say it converges absolutely if the sum of their norm converges, right? Same as in the case of real numbers. And yeah, absolute convergence implies convergence, right? Because if we just let this be the partial sum, then we consider this Cauchy difference, right? Then this will be less than or equal to this, right? Because by triangle inequality, right? Less than this sum, right? This less than or equal to alpha n plus 1 plus da 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 plus alpha n, right? Which is precisely this. This is just by triangle inequality. And if we have absolute convergence, then we can make this arbitrarily small, right? We can make this arbitrarily small because convergence sequences are Cauchy sequences, right? Now some theorem. If a series of real numbers, non-negative, that converges, and if we have each alpha n, the complex number alpha n, its norm is less than or equal to Cn for all n, then this converges absolutely. Well, this is just by some basic comparison, right? The partial sums, this is bounded by assumption. Hence, the partial sum of those are bounded, right? So this converges because the sum of the norm is a monotone series, right? Monotone sequence, right? And we're gonna assume two standard facts about absolute convergence series, which is those. Okay, so I might make a new video about like these two theorems, right? The proof is not easy. Okay, so we first assume them. Okay, so I'll make a separate video on those. And yeah, so first of all is that if a series converges absolutely, then any rearrangement also converges to the same limit. Also, this says that if this converges absolutely for each n, so for each n fixed, and this also converges, right, absolutely convergent, then the order of summation can be interchanged and the series obtained converges the same value. Now we'll talk about functions, series of functions. We define the sup norm. If f is a bounded function, okay, is a bounded function, then we can see that the sup norm is defined, right? And the norm in the sense is that we have the triangle inequality, right? So try to verify this by ourselves using this. And we also have this is true, right? And f is 0 if only if the norm is 0. Okay, f is 0 means that it's a constant zero function. So we can talk about convergence of functions. So given the sequence of functions, we shall say the sequence converges uniformly if it converges under the sup norm. And we say that it's a Cauchy sequence if it's Cauchy under the sup norm. Okay? So here's the theorem. If a sequence of functions is Cauchy, then it converges uniformly. So Cauchy sequence converges under sup norm. Okay, under sup norm. So this is because for each z, we let fz equals to this. So why can we make sure that fnz is converging? Because this is Cauchy, right? So which means that if we fix an x naught, we can make, well, fn x naught minus fm x naught blah blah blah, right? This thing will be less than epsilon, which means that fn of x naught, where n from 1, like this sequence is Cauchy. Is a Cauchy sequence and C, but C is complete, right? So it has a limit. Okay, so for each z, fnz as n goes to infinity has a limit, and we define this new function as f of z. Clear? Because C is complete. Now, given epsilon, we can make this is true for all z because f is Cauchy. Okay, if this is true, if there exists n such that for mn greater than n, we have this is true for any z in the domain S. Given, okay, let this little n fixed. Okay. Now, for any z naught, depend on this. So we're using this. Okay, for any z naught, on this net naught we can pick an m. We can pick this sufficiently large that is greater than n, such that this is true. Okay, because this is true, and we require this to make sure that this is also true, right? So we can do this estimation. So fz minus fn z naught. So we have z minus fn of z naught. We use the triangle inequality. Now, this we just copy down, right? This will be less than epsilon, but this is less than this by definition, right? But we now know that n is greater than n, m is r greater than n, but if we have those, then we have this for all z. Exactly less than 2 epsilon, right? So we see that if we fix an n, if this little n is fixed for any z naught, we can make this less than 2 epsilon, right? Which means that it is uniformly convergent, right? Take your time to digest this, right? So here's a remark. Immediately see that if the functions are bounded, then the limiting function f is also bounded, right? Because as in the proof, we can pick an n such that this is less than 2 epsilon, right? But this inequality here is by triangle inequality. This is less than 2 epsilon, so f of z naught, right? We move this over there, less than 2 epsilon plus mn, where mn is the bound for fn, okay? For all z naught. Okay, so then this mn is the bound for f. So f of z naught less than 2 epsilon plus fn z naught, right? Which is again less than 2 epsilon plus mn, because we can pick a bound for fn, right, if each are bounded. Okay. Okay. So we can consider the sum, right? And we can consider the sum of the functions, right? Converges uniformly exactly means that this converges uniformly, right? Converges absolutely if this converges, right? And recall we have the m test, right? If there's a function such that each of this is bounded by mn for every x, and suppose that the sum of the bound converges, then this is uniformly convergent, right? And I just copied down the proof step by step, right? If you define the partial sum as this, right, then we can estimate this, right, blah, blah, blah. Okay, so we show that this is uniformly convergent. But the thing is that we can also show that this is absolutely convergent. So this also converges. So how do we see this? How do we see this? So if we let Gn equals to u1x plus da 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 plus un, sorry, Gn is this plus da 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 plus da un of x, right? Right. Then Gm minus Gn, right? If we take that, it doesn't matter because, right, it doesn't matter. It will be equals to, I just do it like this plus this, right? But remember, this equality still holds because we have this is less than or equal to mn. Right, so this will still be less than this, right? So this will still be less than that, which means that gnx is a Cauchy sequence in C, right? Our gn here, right? Gn will be a Cauchy sequence in C. Does gn, so define gx equals to this psi. Is it psi or is theta? Psi, right? So this gives a function g. Now, g minus gnx, right? G minus gnx will be equal to, so we, not those, but this, right? Will be this sum. But again, straight up because there's inequality, right? So this summation of unx, right? Sorry, ukx, whatever, should be k, right? Should be k. We still have the bound, right? So exactly, this gives that gx minus gnx less than epsilon for all that. So it converges absolutely. Okay. So if we let a and b a sequence of complex numbers and let r be a number such that the series converges, then this converges absolutely for all z less than r with a norm z less than r, right? Because z norm less than r gives this, which is this less than this, right? Z less than r gives this. So, which means that if we right, so yeah, exactly. If we just to apply the theorem directly, if we let un of z is equal to anzn, then each unz, right, is less than anrn for all z less than r, right? And if this converges, then this converges absolutely and uniformly, which means that this converges absolutely. I mean, yeah, but anyways, right, we get the result. So, okay, so here's an example for the series. For the series, it converges absolutely and uniformly for z bar less than equal to r, right? If you just let cn equals to this, right, then if we took their quotient, it gives you r over n plus 1. If you take n sufficiently large enough, then this will be less than equal to 1 over 2. Then after that, we'll see that, right, therefore there exists a positive integer n naught such that this for some constant c. So this converges because of the geometric series, and we apply the m-test to get the absolute and uniform convergence of this, right? So if we define expz as equal to this, it converges absolutely for all z, right? This converges for any r, this converges for this, which means that we can show that this actually converges for all z, right? And also we know that if we fix z naught, we can find an r such that it contains an enclosed ball, right? And for all this, we know that this is continuous at z. Why? Because all of the quotient, all of the partial sums is a continuous function, right? And we have the uniform convergence, right? So the limit of a uniformly convergent function is continuous, right? Because each of them is continuous, and this is the limit at n goes to infinity, right? So in particular, this is continuous at z naught. So expz is continuous on C. If we fix z naught, is continuous at z0, so it is continuous on C. Okay? So yeah. And similarly, if we define sine z with this expression, cosine z with this expression, they also converges absolutely uniformly, right? So this is like what I did, right? If we just like Cn equals to that, and yeah, with the same steps, we can apply the M test, right? So here's a theorem. Given the power series, if it does not converge absolutely, then there exists a number R such that the series converges for this and does not converge absolutely for Z norm greater than R. So if it does not converge for all Z and complex, then there exists some certain like supremum, some cutoff, such that we have convergence here and we do not converge out there. And the proof is that the series does not converge absolutely for all Z. We define B to be the set of all non-negative number such that this converges. Okay? So we have zeros in B. So B is non-negative, non-empty, right? And we're given that there exists T such that this diverges to infinity, right? Because we said that it does not converge absolutely for all Z, so which meant there exists some Z naught such that AN Z naught N, right? So if we just let Z naught equals our T, right? So this is what I mean by exists a T. The norm of this Z naught is equal to T, such that it diverges to infinity, which means that if U is still greater than T, then U will not be in B, right? Because U is greater than T, then all the AN, UN will be greater than AN, TN. But remember, this already goes to infinity, so this will go to infinity too, right? So if U is greater than T, U is not in B. So if we do the contrapositive, right, T is the upper bound of B. Exactly. What I did is to show that there's an upper bound for B. Right? So if U is in B, then U is less than or equal to T. To exist a T such that it is an upper bound for B, thus a non-empty set that is bounded above has a supremum R. Then it diverges if Z that this is greater than R and converges for all. Okay, so first of all, we know this is true. But do we know this is true? Do we know this is true? Well, first, choose an S such that it lies between Z norm and R, right? And by comparison test, because S is in B, right? We have this converges, right? Which means that this is in B. So our assertion follows. So there exists an R such that for all this, it converges. And for this, it diverges. Okay? So this R is called the radius of convergence of the power series. If the power series converges for all Z, we say the radius converges to infinity. If it's 0, then we say the radius is 0. A power series has a non-zero radius of convergence is called a convergent power series. Okay? If this is a disk and a center at the origin contained in the disk this, where R is a radius of convergence, then we say the power series converges on D. Okay? Now, we're gonna move on to some formula of the radius of convergence. We know that it exists, right? So at least first of all, we show that the radius of convergence exists. Now, it can be determined in terms of coefficients. So first, let's just start with a sequence of real numbers. Remember, the limit point is a sequence of number of this sequence is a t such that for any epsilon, there are infinitely many n such that it lies in the epsilon neighborhood of t. If it's bounded, it has a limit point, right? bounded sequence has a convergent subsequence, and the limit of the converging subsequence is exactly the limit point, right? This is a Bolzano-Weierstrass or Weierstrass-Bolzano, or you can argue this by bounded sets, they're like bound sequentially compact, right? Or whatever, right? Compact, sequentially compact, limit point compact, same thing. So if you let S denote the set of all limit points, we define lambda as the supremum of all limit points. Such definition makes sense because the sequence is bounded. You cannot have the limit point that goes to infinity. Right? So we can define lambda as the supremum of all the limit points. Or is all the set of all subsequential limits. Right? So with the same notation above, we see that this supreme of S, lim sup actually lies in it. And the proof is just by some standard argument, which will be skipped. Okay, we know that it lies in Z. And also it has a property that is given epsilon, there exists only finitely many n such that it is, so if we draw a diagram, lambda, for any epsilon, right, there will be only finitely many Tn that lies outside there. And there are also infinitely many n such that it lies in here, right? Only finitely many out here, but infinitely many here, right? And conversely, if S satisfies these properties, then S is equal to lambda. S is the lim sup. So if there were infinitely many n such that Tn is this, we suppose by contradiction, right? If there are infinitely n such that this is true, well, because the sequence is bounded, it will have a limit point, right? So if we have this lambda, this epsilon, and because it is also bounded, so it must be stopped somewhere, then we have infinitely many points here, right? Then it will have a limit point that lies entirely outside of here, which is greater than lambda. Contrary to the assumption, we'll assume lambda is the sup, but x is in the limit point. This is the supreme limit point, right? And on the other hand, right, this is, I believe it is clear, right? Because I believe this should be clear for you, right? Why? Because lambda here, lambda minus epsilon, then by definition, we can pick an x, right, where x is the limit point of Tn's, right? So there will be infinitely many Tn eventually lies in this neighborhood, right? And conversely, if we assume S is not equal to lambda, then without loss of generality, we can first assume this. We can assume this is S and this is lambda. We can pick x and S such that this is true, right? We can pick x here. Well, simply, we can see that there will be infinitely many n, right, lies in here, right? Right. But remember, as x here, there will be infinitely many Tn that lies in here, which is what? Greater than S, right? So Tn greater than equal to, there should be a greater than equal sign, S plus epsilon for some, just the epsilon be the midpoint between, the distance between S and X over 2, so it will be here, right? This is the distance. Right, so it will be infinitely many here, right? So done. So this proposition gives an equivalence condition of lim sup. And for convenience, if the sequence is not bounded above, we just set the lim sup to be infinity, okay? And we have these three, these three theorems if we have both sequence of real numbers, okay? So to prove it one by one, we'll just prove the first one, okay? Okay, so if one of the sequences are bounded, then inequality holds because one has the infinity, right? So assume that now both sequences are bounded. Then the sequence is also bounded, right? The sum is also bounded. Suppose that for a contradiction, this will be greater than t plus s. Suppose the lim sup of this is greater than t plus s. We want to get a contradiction because this is what we want to prove. Well, since u is the limit point of this, right? U is the limit point of this, which means, why is the limit point? Because the lim sup lies in the set of limit points. Remember? U lies in the set of those. So it is indeed a limit point. There will be an epsilon greater than 0 and infinitely many n that has, this is true, right? Because this is u, this is t plus s, right? So, oh, sorry. This is t plus s, and this is u, right? U is greater than that, so there will be infinitely many n such that it lies in here, right? But remember, there are only finally many n that has, this is true, and all you did, this is true. So we're taking the intersection of those finally many n's that gives only finally many n that has, this is true, right? A contradiction. We assume that we have there infinitely many, but in fact there's only finally many. So this is a contradiction. So for the product, it's actually similar. Maybe you take a look at it. And for the third one, if the sequence converges, then the limit is equal to the lim sup, right? Because if the sequence converges, all the subsequence converges to the same limit. The set of limit points is a singleton set. Thus, the supremum is the point itself, right? So finally, we come to a theorem that states the precise formula of the lim sup, which is if r is the radius of convergence, then 1 over r is equal to this. Okay, so hold on. In the denominator, if the sequence, so here's a, if the sequence is not bounded, r is 0. If the lim sup is 0, then r is infinity. Okay? So first, we let t equals to this and suppose that t is not 0 or not infinity, right? And then the proof follows. Right, for epsilon, there is only finally many numbers such that this is true, which means that only finally had this, which means that there are all but finally many that has this. And we raise it to the power of n on both sides, right? Thus, if we just multiply z to the n, norm z to the n, like is this, for all but finally many n. Now, we just require norm z less than 1 over t plus epsilon, right? If this is true, then z times t plus this will be less than 1, right? This will be less than 1, which means that this n, right, if this time t plus epsilon is less than 1, then this geometric series will converge. And by the comparison or m-test or whatever you said, right, the series converges by comparison, like this converges absolutely, right? So the radius of convergence r satisfies this, right? Because for all this, the series converges. For all this, the series converges, which means that the radius of convergence r should be greater than or equal to this. For every epsilon, thus we have this. Conversely, given epsilon, there's infinitely many n such that this, remember? And we have the same argument, right? Because it diverges, so it also like something divergence, right? And we discussed t0 or t infinity. It is quite simple, so I just leave it here for you to read through. Also, if it converges, then r is equal to 1 over t, right? Suppose that the radius converges greater than 0, then we have a number C and A such that this is true. It's just some corollary, okay? Some corollary. And here is the ratio test. So this ratio test allows us to compute the radius of convergence easier. So given a sequence of real numbers and assume that this exists, right? So if this limit exists, then this limit is precisely the radius of convergence. Okay, so I'll leave you to read through the proof here. Okay, I'll leave you to read the proof here. It is quite technical. It's just by comparison. It's all by comparison, right? Thus, we have an example for the binomial coefficients. Okay, we define the binomial coefficients like this in a binomial series. Okay, the radius of convergence is equal to 1 if alpha is not equal to an integer. So if alpha is not equal to an integer, right, then none of the coefficients are 0, right? Right? And then we apply the ratio test. And this limit is equal to 1, right? Alpha minus n plus 1. As n goes to infinity, alpha minus n plus 1. How do you evaluate this limit? Well, you divide n on the top and bottom. So it will be alpha over n minus 1 over 1 plus 1 over n. So this thing goes to 0, right? And this thing goes to 0. So it will be negative 1 over 1, but remember we're taking norm, right? So yeah, that is the sum application. Okay, so this is it for this lecture, and I'll see you guys next time.